We are constantly used to seeing the physics of chemical propulsion, with fire and noise, rockets burning their way into orbit. We've even talked about the immense power of nuclear fission engines.
Yeah, those are impressive in their own right.
Definitely. But today, we are kind of skipping the familiar. We are moving beyond current engineering limits and plunging into the concepts that represent, well, the next great leap in interstellar velocity and power, bridging that vast gulf between current reality and genuine science fiction.
Right. Our mission today is really all about limits. The current systems we rely on, even the most advanced ion thrusters, they're great for navigating our immediate neighborhood.
Sure, for Mars trips and things.
Exactly. But if you want to cross the solar system rapidly, or if you harbor any dream of reaching the stars in a meaningful time frame, you need fundamentally different physics. We are looking at stellar power in a bottle fusion, and then we're tackling the ultimate challenge, traversing space-time itself through faster-than-light concepts like the warp drive.
Okay, let's unpack this enormous topic. We have a set of sources that walk us from the cutting edge of propulsion engineering right to the very edge of theoretical physics. Our mission, then, is to understand how we might harness the energy of a sun, and then maybe how we might break the rules of the universe. Let's begin with fusion rockets. Fusion. It's almost universally seen as the ultimate energy source, right? The exact process that keeps the lights on across the cosmos.
Pretty much, yeah.
And when applied to propulsion, our sources show this offers performance that simply dwarfs everything else we have.
It truly does. To really grasp this performance difference, we need to focus on one key metric: specific impulse, or ISP.
ISP, right? Fuel efficiency, basically.
Exactly. Think of ISP not as raw speed, but as the fuel efficiency of the rocket. How much thrust you get per unit of fuel consumed over time, measured in seconds. A powerful conventional chemical rocket might get you, 450 seconds of ISP?
No one, yeah.
And a highly optimized nuclear thermal rocket maybe hits about 1,000 seconds.
Okay, so 1,000 seconds is already double the efficiency of a standard chemical engine. That's significant.
It is. Now, picture fusion rockets. These could theoretically achieve specific impulses in the tens of thousands of seconds.
Tens of thousands.
Yeah. You're moving from like a standard sedan to something with the fuel efficiency of a bicycle, but the power of a semi-truck. It's a different league. That massive leap in efficiency is what makes rapid, deep space travel potentially possible.
That is just astonishing. And the exciting part is that this isn't purely theoretical musing anymore. There are real-world, funded concepts being developed right now. Tell us about the direct fusion drive.
Yes, the direct fusion drive, or DFD. It's currently, you could say, the darling of advanced propulsion research. It's a groundbreaking concept funded by NASA, designed to produce both thrust and electrical power directly from a compact fusion reactor.
Thrust and power, that's handy.
Very. It's based on the Princeton Field Reverse Configuration, or PFRC, fusion experiment.
PFRC, okay, that's a bit of a mouthful. For listeners trying to visualize this, what does a field reverse configuration actually mean in practical terms? How's it different from, say, a tokamak?
Good question. So
Yeah.
most big fusion reactors, like the giant ITER project in France, use donut-shaped tokamaks for confinement. The PFRC uses a linear, kind of cylindrical geometry. In the setup, the plasma itself, the superheated fuel, generates its own magnetic field that actually reverses the direction of the external field. It basically confines itself in a compact, stable magnetic bottle.
Huh, self-confining.
Yeah, and that potentially small, high-density confinement is key to maybe reducing the overall size and mass of the whole system, which is crucial for space travel.
Makes sense. And what technical breakthrough lets them keep that plasma stable enough to sustain thrust? Because stability is always the big fusion challenge, right?
Absolutely. The secret sauce, as they call it, is a specific method of radio frequency heating called odd parity heating. This technique seems to be what allows them to maintain stable plasma confinement within that specific configuration. If you can keep the reaction stable, well, you can keep the thrust flowing.
Okay, odd parity heating. Got it.
Now, let's look at the real-world impact of this, say, 9,600 second ISP performance. Our sources detailed a theoretical mission study to Sedna.
Sedna's way out there, past Neptune.
Out there. It's a dwarf planet candidate, a trans-Neptunian object. Its closest point to the sun, its perihelion, is 76 astronomical units away. That is seriously far out.
76 AU. Just for perspective, Voyager 1 took decades just to officially leave the solar system, roughly defined. A conventional probe mission to Sedna using current propulsion. Chemical rockets, gravity assists. That would take around 30 years.
30 years, yeah. Now, with the DFD, assuming a 1.6 megawatt system, which is relatively compact for a fusion reactor, that trip could potentially be completed in approximately 10 years.
10 years instead of 30? That's a huge difference.
It is, and crucially, the total amount of time the engine would actually need to be thrusting is only about 1.5 years out of that 10.
I mean, hang on, 10 years. It sounds revolutionary compared to 30, definitely.
Oh.
But it still feels kind of slow, given we're talking about harnessing stellar power here.
Oh.
Why is it still a decade-long trip?
That's the engineering reality check hitting us. Even with that amazing 9,600 seconds of ISP, you're only generating about 8 newtons of thrust in this specific 1.6 milli-dB model.
8 newtons? That's tiny, like the force to hold up a couple of apples.
Pretty much, yeah. It's a very gentle push. But here's the key. Because the fuel consumption is so incredibly low, we're talking maybe 0.3300 kilograms of helium-3 propellant for the entire mission.
Just 300 grams?
For the whole trip. So you can afford to thrust continuously for months, even years. It's incredibly slow acceleration, but it's constant acceleration over a very long time. And that ultimately gets you there much faster than any short, powerful chemical burn followed by coasting or complex gravity assist could manage for such a distant target.
Okay, that context is vital. It's the tortoise versus the hare,
Yeah.
but the tortoise has an almost infinitely deep fuel tank.
Very good analogy, yes.
And we've come a long way conceptually. I mean, we went from early fusion concepts like Project Daedalus back in the 1970s. Wasn't that thing supposed to weigh 54,000 metric tons? Just insane. And like 92% of that was propellant.
Yeah, basically a small battleship made mostly of fuel.
Just for a 50-year one-way trip to Barnard's Star. Then
Yeah.
we shrunk that down a bit for Project Longshot in the late 80s. Still a 400-ton beast aiming for a 100-year trip to Alpha Centauri.
Still huge. Still incredibly long travel times.
So the DFD, conceptually at least, represents this massive theoretical collapse in required mass, fuel, and time compared to those behemoths.
Absolutely.
Yeah.
But, and here's the current reality we still face. Despite the stunning theoretical performance, current fusion technology still struggles with major engineering roadblocks.
Like what specifically?
Well, the equipment needed to safely contain and sustain that superhot plasma is still just too heavy for practical deep space launch and long-duration missions. And maybe more fundamentally, the energy ratio, the energy you need to pump in to start and sustain the fusion reaction versus the energy you actually get out, is still too small for many concepts.
Q factor, right. Getting more energy out than you put in.
Exactly. That limits continuous fusion duration today. So the physics works on paper, maybe even in brief lab experiments, but the engineering is still wrestling with the scale, the mass, the power efficiency, the cooling, all of it.
That perfectly sets up our pivot then. We've sort of reached the limits of current foreseeable engineering, the fastest we can realistically hope to go within the known laws of physics using reaction mass. Now, let's turn to the ultimate speed limit, the speed of light itself. All our travel results, everything we've discussed, are currently bounded by that cosmic brick wall, at least for observers back on Earth. Can theoretical physics offer, well, a loophole?
That speed limit, roughly 300,000 kilometers per second in a vacuum, it's arguably the most fundamental constraint of our universe as we understand it. But yes, general relativity, Einstein's theories, which governs gravity and the structure of space-time, does offer a theoretical possibility. The Alcubierre Warp Drive.
The warp drive. And it's fascinating that this concept was directly inspired by science fiction, isn't it?
It absolutely was. The term warp drive itself actually originated way back in John W. Campbell's 1931 novel, Islands of Space, believe it or not.
Yeah, that early.
Yeah. But its modern visual identity, the whole concept, was really cemented by Star Trek. When Miguel Alcubierre, the Mexican mathematician, published his foundational paper back in the 1990s, he explicitly stated it was inspired by the show's terminology and concept.
So how does this fictional idea actually become mathematically, well, plausible under general relativity?
Okay, so general relativity tells us that gravity isn't really a force, but the manifestation of space-time curvature. As John Wheeler famously put it, quote, "Space tells matter how to move, and matter tells space how to curve."
Right. Mass bends space-time.
Exactly. The Alcubierre theory involves creating a highly localized, artificial distortion of space-time, what we call a warp bubble, around the starship.
So the ship isn't actually moving through space faster than light? The space around the ship is moving, is that it?
Precisely. That's the core idea. You are contracting space-time in front of the ship and expanding space-time behind it. The ship itself remains essentially stationary within its localized bubble, moving at perfectly normal sublight speeds relative to the bubble walls immediately around it. But because the fabric of space surrounding the bubble is being manipulated, contracted, and expanded, the bubble, and therefore the ship within it, effectively traverses the distance faster than light relative to a distant outside observer, all without violating local physics inside the bubble.
Okay, that is truly mind-bending stuff, but I sense a but coming. Every massive physics loophole seems to come with an equally massive cost or requirement. What is the fuel, so to speak, required to create this universe-bending bubble?
You sensed right. The main and really enormous requirement is something we collectively dub exotic matter. This isn't just standard matter or energy. The drive requires regions of negative energy density or perhaps negative mass.
Negative energy density.
Yes, and this is the exact same highly theoretical kind of material that wormhole theorists also suggest is necessary to prop open a traversable wormhole, to hold its mouth open and keep it stable long enough for something to pass through.
Negative energy density. Okay, that sounds like something you just invent in the math equations to make them balanced, doesn't it? Does it actually exist anywhere outside of a theoretical physicist's whiteboard?
Well, mathematically, quantum field theory does permit it under certain special, very limited circumstances. The one tangible, known, experimentally liquefied example we always cite is the Casimir effect.
Ah, the Casimir effect, where two plates close together.
Exactly. Two uncharged conductive plates placed incredibly close together in a vacuum. Quantum fluctuations in the vacuum between them are slightly suppressed compared to the fluctuations outside, resulting in a tiny but measurable net attractive force. This region between the plates technically has a lower energy density than the surrounding vacuum effectively, a negative energy density relative to the vacuum outside.
Okay, so it can exist, but the Casimir effect is microscopic, right? We're talking about generating negative energy density on a scale large enough to enclose an entire starship. Isn't that just fundamentally unrealistic based on what we know?
That is absolutely the multi-trillion-dollar question. That massive leap in scale is, well, daunting, to say the least. And even if we could somehow conjure up enough exotic matter, critical challenges and showstoppers immediately arise when you try to actually use this drive to achieve superluminal, faster-than-light velocities.
Okay, let's talk about the downsides then. Before we get too carried away plotting courses to Alpha Centauri, what are the theoretical traps here? The things that might make this impossible?
There's a famous, quite critical semi-classical instability argument that emerged around 2009. It basically suggests that FTL velocities using this kind of warp bubble are likely impossible in practice.
Why? What happens?
Because the bubble itself would likely be destroyed, or at least destabilized, by something called Hawking radiation.
Hawking radiation, like the kind associated with black holes.
The very same. The intense curvature of space-time required to create the warp bubble, especially at the leading edge where space is being compressed, would generate extremely high temperatures inside the bubble due to quantum effects at the event horizon-like boundary.
So it cooks itself.
Essentially, yes. These incredibly high temperatures, generated by particles popping into existence at the bubble walls, would probably destroy the bubble itself, and would certainly incinerate anything unfortunate enough to be riding inside. A catastrophic, self-immolating system.
Right. That sounds like a definite deal breaker for passengers, yes. So the universe's ultimate speed limit seems to defend itself rather aggressively.
It certainly appears that way. However, there is a fascinating little silver lining noted in that same research. These extreme heat and destabilization problems seem to be completely absent if the warp bubble travels slower than light subliminally.
Slower than light. So what's the point then?
Well, it would still be an incredibly efficient propulsion system, potentially far exceeding even fusion rockets in terms of energy use for a given delta V. It still requires that exotic matter, which is the huge hurdle, but if you had it, a subliminal version might be stable and incredibly effective for fast solar system travel, even if it can't break the ultimate FTL barrier.
Interesting. So maybe a warp drive within the solar system, but not between stars.
Perhaps. But we still have that exotic matter problem. What if we can't find the negative energy density needed? Could we maybe just make the drive less demanding on the energy front somehow? Is there an engineering fix for what seems like a fundamental physics problem? That's where some more recent research offers an intriguing potential mitigation. Analysis has shown that the total amount of energy required for the drive, including the amount of negative energy, can apparently be greatly reduced simply by changing the geometry, specifically by allowing the wall thickness of the warp bubble to increase.
Wait, the wall thickness? That seems like an almost anticlimactically simple engineering tweak to help solve a monumental physics problem. Just make the walls thicker.
It sounds simple, but it highlights the weird nuances of general relativity. Geometry is gravity, is space-time.
Hmm.
If you manipulate the geometry in specific ways, the mathematical demands on the exotic matter change, sometimes drastically. Thicker walls mean gentler curvature gradients, apparently.
Yeah.
But even with those potential mitigations, it's important to note that very recent studies, like from 2022, still concluded that even these modified, potentially lower energy physical warp drives seem to violate something called the null energy condition.
Okay, the null energy condition.
Mm.
Simplified for us non-physicists, what does that mean?
It basically means that even with the tweaks, the drive still fundamentally requires mass or energy behaving in ways that are impossible or highly improbable, according to our current, well-tested understanding of physics. It implies negative energy density is still needed. We haven't really solved that core exotic matter problem yet, even if we could reduce the amount needed.
So the jury is still very much out. Fascinating, but maybe not happening tomorrow.
Not tomorrow, no. Now, the Alcubierre drive concept is closely related, mathematically at least, to the theoretical reality of wormholes, or Einstein-Rosen bridges, as they were originally called. These also stem directly from solutions to Einstein's equations in general relativity.
Right, tunnels through space-time. So if we could somehow find the technology or the exotic matter to make a warp drive work, could we also potentially make a wormhole?
Mathematically, the requirements look very similar, yes. Just like the Alcubierre drive, actually creating a traversable wormhole, one that stays open long enough for something or someone to pass through, is thought to require that same persistent negative energy density, that exotic matter.
There it is again, the magic ingredient we don't have.
Exactly. Without it, theoretical wormholes tend to snap shut faster than light could cross them, making them useless for travel.
Okay, now let's differentiate all this theoretical physics warp drives, wormholes, from a term we hear all the time in sci-fi, hyperspace. How is that different?
Ah, hyperspace. That term, coined again way back in 1931, is strictly a narrative theme, a science fiction trope. It doesn't really have a basis in current theoretical physics like the Alcubierre drive or wormholes do, however speculative they are.
So it's just a storytelling device.
Pretty much. In science fiction, it usually functions as a kind of specialized alternate dimension or parallel space that allows ships to take a shortcut between distant points in our normal space.
It's often depicted visually as like folding space, right? Or jumping into a different kind of reality.
Exactly. It's often visualized as the idea that our familiar three-dimensional space can be somehow folded or crumpled through a higher fourth or fifth spatial dimension, bringing distant points effectively close together for rapid transit. Unlike the warp bubble and wormholes, which are actual mathematically derived, if highly problematic, solutions to Einstein's field equations, hyperspace remains primarily a creative narrative device for hand-waving away the vast interstellar distances and the light speed limit.
Got it. Physics versus narrative. Useful distinction. Wow. We have covered a colossal range today. On one side, we have the tangible, if challenging, engineering reality of things like fusion engines, like the DFD megawatt power, promising maybe 9,600 seconds of ISP, potentially turning a 30-year trip into a 10-year dash across the solar system. That's engineering pushing right up against the known limits of physics.
Right. Real materials, real plasma physics, real engineering hurdles like mass and efficiency. And then on the complete other side, we have the mathematical elegance, the sheer mind-bending possibility, but also the profound theoretical roadblocks of STL travel concepts like the Alcubierre drive. And what's fascinating is how they highlight this common boundary we keep hitting, whether the challenge is reducing the sheer mass and increasing the efficiency of a compact fusion reactor, or somehow finding or creating that elusive exotic matter needed for a warp drive or a wormhole. Both pursuits ultimately hinge on testing the fundamental boundaries of general relativity itself and our understanding of energy and space-time.
That really ties it together. It's all about pushing those boundaries. So here's where it gets really interesting for you, the listener, to think about. If the immense, perhaps astronomical energy requirements for a theoretical warp bubble can apparently be greatly reduced simply by allowing the wall thickness of the bubble to increase a geometric tweak, what other creative, maybe non-obvious geometric manipulations or perhaps minor adjustments to our fundamental assumptions about space-time and energy could potentially open up the path to the stars without needing unobtainable magic like huge amounts of negative energy? What other loopholes might be hiding in the math? That's definitely something to ponder long after this deep dive is over.